Assalamualaikum. Very good morning to all of you. So today we're going to continue with a lecture on new chapter. So the new chapter is on magnetic material and influence. You can refer to this slide. This is an excerpt from the course information. So basically for this week, number 10, supposedly, in which it is from 19 December to 23rd of December. So this will be the topics they're going to cover. So the first part of this chapter will be on the topics of magnetic force. So this will be the main topics for this slide. And followed by this will be on the magnetization and also the effects of magnetization. So this will be on a magnetic material topics and followed by boundary conditions between magnetic materials. So basically there will be three main topics in this chapters of materials and influence that will be covered in this week number 10. Okay, so as mentioned before, we will be covering the topics of magnetic force, which will be the main discussion in this lecture number 18. Okay, so let us proceed with lecture 18, which will be the topics of magnetic force. So reference for this lecture 18, you can get it from Sadiko, page 352 to page 364. So the motivation of this lecture 18 is to demonstrate the force exerted by the magnetic field. Okay, so let's have a review on the force that we have learned previously in chapter 4, if we can refer to chapter 4 topics, which is on the potential, on potential. And in potential chapter, we have learned about the force. Okay, if we can recall, if we have this point charge of Q, and the point charge of Q is said to be applied with the external electric field E, so we can say that there should be a generation of force, which is given by this equation, F equals to Q of E, which is basically the formation of, it is formed based on the Coulomb's law principle, F equals to Q of E, which is the force produced on the charge of Q due to the application of external field of E. So that should be the force produced, or the force which is experienced by the charge point of Q. And it is measured in terms of Newton unit. So the same things applied in the case of magnetic field case, in which if we have a current, in this case we have a filament current structure, we have I, and the filament current is said to be exerted by the external magnetic field B. Okay, and B is also known to be a magnetic flux density. We have just learned it in previous lecture 17. So we can see that for this particular case, this current element dl, this current element of dl will be said to experience a magnetic force, which is given by this equation, in which the force experienced by a small element of current, in this case is I dl vector, will be given by this equation, where the dm vector is equals to I dl cross B, where I dl is the element of the current, and the B vector is the external field, magnetic field, which is said to exert the force, this particular current element of I dl vector. Okay, so this is the equation of magnetic force, which is also measured in Newton, and we can see some difference between the electric force that we have seen previously and also the current our current discussion on the magnetic force. So this will be the difference between the force that we have mentioned, that we have discussed previously in electrostatic, and the current discussion on the electrostatic force. So we have F equals to Q of E for the case of electric force, and we have dF equals to I dl cross B for the case of magnetic force. Okay, so let's have a look at this slide where we have two infinite and parallel filament current, where we have both current are said to be parallel. We have I1, current is directed towards a positive Z direction, and we have I2 current, which is directed towards a negative Z direction. And both currents are said to be separated by a distance of d. Okay, and in this particular case, we are trying to calculate what should be the force per unit length. Yeah, force per unit length between these two conductors. Okay, so looking back at what we have discussed previously from the previous slide, we can see that the force experienced by these particular conductors. In this case, we are calculating the force experienced by this element of dl2. So we can see that from the equations of the F vector equals to I dl vector cross B, we can see that I dl vector is this element, while the B vector is the element, B vector is basically the field, the magnetic field which is produced by the I1 towards this element of I dl2 vectors. Okay, so for that particular case, we can see then that from these equations, we can rewrite that the I dl vector can be written as I2, and the dl vector can be written as dz in the direction of negative z. That should be the case, yeah, because your current is directed towards a negative z, so then we're going to have the dl to be dz of negative z direction. And basically the B vector, which is our field density produced by the I1, can be written as this cross product. Yeah, so we're going to have mu naught of H field. Yeah, because we have learned that B equals to mu of H for the case of free space environment. So we're going to see that that will be dF of I2 of dz of negative z direction. Okay, and then we're going to have mu naught and H. Because this filament I1 is infinite in length, so we're going to have H to be I1 divided by 2 pi of D. So because we have equation previously, we have H equals to I over 2 pi R in the free direction, yeah, which is the H field intensity produced by any filament with infinite length, whereby R here is a radial distance from the filament to the point of interest. So in this particular case, since the distance, okay, the perpendicular distance, yeah, the normal distance from the I1 to this element is given by D, so we can just substitute the R to be equals to D. And in terms of the current phi, in terms of the field direction, yeah, field direction, the phi that can be written as the current cross the R. So we're going to have that the current cross the R, yeah, from here we're going to have L cross R. We have L equals to, L is a positive Z direction. Yeah, because your I1 is directed towards positive Z, and the R basically will be the Y. Yeah, so Z cross Y will give us negative X direction. So that will be the substitution for the new vector of phi for the H field just now. So we're going to have the equation will be mu naught I1. Yeah, sorry, if I can rewrite it. Okay, so we're going to have it as I2 dz of negative z cross product with mu naught I1 over 2 pi of d, and L cos R will give us negative of X direction. So the rest will be just a cross product. Yeah, will be just a cross product. Yeah, and up we're going to have from here that the dF, yeah, the dF will be then written as mu naught I1 I2 divided by 2 pi of d. Okay, and then we have a dz then. So negative z cross negative x will give us positive 1. Yeah, right. So that should be the result of a dF. But since the question asks us about the force per unit length between the two conductors, yeah, remember this is the force that is produced by that is said to be experienced, yeah, by the element of dl2 here. So that should be the force term, yeah, the force term, which is said to be experienced by the dl2 element. So we can find the force per unit length by simply uh, bring the dz to the left. So from this equation, you're going to have df vector over the dz, you're going to have mu naught I1 I2 divided by 2 pi of d in the direction of y. So that will be the force per unit length in the units of Newton per meter. Okay, so that should be the answer for this question, yeah, which is to calculate the force per unit length, right? So this is the things that we have it as the answer here. So we have discussed it earlier then, right? So um, this is more general terms of the force. What we have here is the force per unit length, a force that is said to be produced on a filament current. So that's why we have the element here is the element of current element, filament current element, so IDL vector. And we can also obtain the force on a surface current by simply change the IDL vector into the GS vector ds. And similarly, we can also calculate the force on the volume current by simply substitute the IDL vector into the J vector dB, which are the element for the volume current, yeah, element of the volume current. So we have discussed about this element of the current in lecture 15, which is the very first lecture on the electrostatic field, yeah, right? So this is all about the force or magnetic force that experience or that can be produced on the filament current, yeah, that will be produced on the surface current, or that can be produced on the volume current. Remember that all the B here, all this vector of B basically are the external field density that is exert, that is said to exert the force on that particular current element. Yeah, right. So let's have a look on this example number 1 on the force, where we have a rectangular loop carrying current of I2, which is said to be placed parallel to an infinitely long filamentary wire carrying current I1 as shown in the diagram here. So we need to find the force experienced by this particular loop of red colored here. Yeah. Okay, so in order for us to find the force experienced by the loop, what we can do is that we can separate this loop into 4 different sides. So we have side number 1, side number 2, side number 3, and side number 4. So what we have to do is that we need to calculate the force experienced by each side. Side 1, 2, 3, and 4, and subsequently we can add the resulted force experienced by these sides to get the total force experienced by the loop. Yeah. Okay, so let us do it one by one. Let's say we do it for side number 1. Side number 1 here. So for side number 1, because this is related to the filament current, so we can still use the equation on the force element. The force that is said to be exerted on the current element, filament current element. So we're going to have dF vector should be equals to I dl vector cross B. Yeah, that should be the equations used in this case. So for side number 1, looking at the side here, we know that your current is directed here. This is your current direction. Yeah, remember this is your current direction. So similarly for side 1, that should be the direction of current. So we're going to have it as I2, and the dl vector should be dx, direction of x. Yeah, because we are taking that this side number 1 is parallel to the x-axis. So we can simply take that the dl will be dx to the direction of x. Whereas for the B vector, which is produced by this I1 to the element 1, then we can have it as mu naught of I1 divided by 2 pi of x in the direction of phi. Okay, so looking at these equations of B, which has been written here, is that I'm taking that the radial direction, radial distance, radial distance from the I1 current, which is infinite in length, to site number 1 here is taken to be x. It is taken to be x because why? Because we can see that for site number 1 here, we have a length from this point here, this point. So all the point here we have numbers of points from R0 to R0 plus A. So basically we can just take it as x, whereby x here is a general distance within this site 1. Why I'm taking x is a variable because it is parallel to the x-axis, so we just take it as x. So x basically is a variable, a radial distance from I1 filament to any point on site 1. So from here we can proceed with the calculation of force. So we're going to have dF. Before that, we need to change the phi. Then phi should be changed. So we're going to have current cross R. So we're going to have that current is towards positive Z, and R direction, if we base on this, it should be in X direction. So basically Z cross X will give us Y direction. So that should be Y direction for the B vector then. So we're going to have it as a mu naught I1 I2 over 2 pi X dx, and X cross Y will give us a Z direction. So from here we can have the force, the total force experienced by site number 1 to be equals to integrations of mu naught I1 I2 over 2 pi of x dx in the Z direction. So that will give us mu naught I1 I2 over 2 pi integration of 1 over x dx in the Z direction. So from here we know that the x will be having a range from R0 to R0 plus A, and from here we're going to have that the force will be then equals to mu naught I1 I2 over 2 pi ln of R0 plus A divided by R0 in the Z direction. So that should be the force experienced by site number 1. And if we can have a look based on this equation of F, we can see that the force is towards the Z direction, in which if we base on this diagram, we can see that the force is in this direction, which is said to be pulling away, pulling away the site number 1 from the structure. Okay, so that should be a force experienced by site number 1. Okay, so let's have a look at site number 2. Site number 2. So for site number 2, we're going to have the equations written as dF equals to I dl vector cross B. The similar equation shall be applied. So we're going to have it as I2, and the dl should be in this direction. And from here, we know that the dl should be dz in a negative Z direction, cross product with B. So B basically will be the field density produced by the I1 to this particular site number 2. And if we base on this, we can see that all the points located on site number 2 will be having similar perpendicular distance. From the starting point here up to the end point here, all the points within this site number 2 will be having similar perpendicular distance, which is R0 plus A. So we can simply write the B to be mu naught I1 over 2 pi in the bracket R0 plus A, which is a constant distance. And we're going to have a phi angle, in which we can just write the phi to be equal to the current cross the R. The current will be in the Z direction, and the R will be in the X direction. So Z cross X will give us Y in the vector. So that should be the replacement for the phi in the vector there. And from here, we're going to have the dF to be mu naught I1 I2 over 2 pi R0 plus A dz. And we have negative Z cross positive Y. We're going to have it as positive X direction. And end up we can proceed further with the integration to find the force on site 2. So Okay, so F, the total force on side number 2 will be integration of dF, which will be integration of mu naught I1 I2 over 2 pi R naught plus A dz in the x direction. So that will give us z range, which is from 0 to B. Okay, that should be the range of z. You have to have it as mu naught I1 I2 over 2 pi R naught plus A B in the direction of x. Okay, so that should be the force experienced by side number 2. Again, if you base on this equation of F, we can see that the force is directed towards positive x, which is again, it is pulling away side number 2 from the structure. Okay, and from side number 3, the discussion will be almost similar to side number 1. So I will just base on this sketching for side number 3 then. I'm changing it to side number 3 now. So I'm going to use red colored marker to put any difference on side number 3 calculation. So again, we're going to have similar terms, but there should be some changes basically on your IDL vector, that direction, in which if you base on the direction of the current, it should be directed towards negative x. So we're going to have it as dx of negative x. Yeah, so the dl should be dx of negative x direction. Okay, the rest will be the same. Yeah, b will be the same because we shall just use the distance of x, which is a perpendicular distance for any point on this side number 3, which is similar to our discussion in side number 1 before. Yeah. So again, the direction for the field will be changed to be then written as y. Okay, and for that we're going to have the force as given here in these terms, but there should be changes on the direction of the force, in which negative x cross y will give us negative z direction. Yeah, so that should be negative z direction also. Yeah, few things need to be changed here, right? So that should be negative z direction, and that should be negative z direction also. In terms of the integration will be similar, whereby the x will be having a range from R0 to R0 plus A, and end up going to have this equation for the force, except that the force will be having different direction, which will be towards negative z. So from here, we can see that the direction of the force will be in this direction. Yeah, with this direction. Again, it will pull away side number 3 from the structure. Okay, and finally for side number 4, the discussion will be similar to side 2 just now. So I'm going to use side number 4 then. So for side number 4, which is the closest side with I1, yeah, so we're going to have the DL vector will be having some changes there, whereby the DL will be in a positive z direction. Yeah, positive z direction, because we can see from here the current is directed towards positive z for the I2 current. The rest will be the same. Yeah, rest will be the same, but just to make sure that you are clear about this, the distance will be shorter then. Yeah, because previously for the side number 2 it is R0 plus A, but now for side number 4 simply it is R0 only. Okay, so we're going to have R0 only for a perpendicular distance, yeah, from I1 to I2. Yeah, and the rest will follow then. So need to erase few things then. So that should be R0 and R0 only. So that should be R0, and that should be also R0, and that should be R0 only. So the rest will follow. So Z cross Y will give us negative X. So remember, that should be negative X direction. Okay, so that should be the answer for the F, for the force on side number 2. Again, if you base on this equation, the force on side 4 will be directed towards negative X, which is again pulling away side 4 from the structure. So this will be the force experienced by side 1, 2, 3, and 4. And for us to find the total force, so simply we just add force due to side 1, force due to side 2, force due to side number 3, and finally force due to side number 4. So that should be the total force produced on this loop, yeah, due to I1 current. Okay, so let's have a look at example number 2 for the force calculation. We are given in this example a three-phase transmission line consists of three conductors that are supported at points A, B, and C to form an equilateral triangle as shown below. So at one instant, conductors A and B both carry a current of 75 milliampere, while conductor C carries a return current of 150 ampere. Okay, so let's have a look at this particular questions then. So this is equilateral triangle, means that from A to B is 2 meters. Also from A to C is 2 meters. And from B to C is also 2 meters. So this is what we call as equilateral triangle. Conductors A and B carry 75 amperes current. Okay, conductor C carries 150 current. Yeah, return current means that this is direction. If you base on this sign, current for conductor C is pointing inward, right? Is pointing inward, while current at conductor A and B is pointing outward. Means that if this is X, Y, so A and B is directed towards Z. Yeah, this is Z direction. Yeah, A and B is directed towards positive Z, while conductor C is directed towards negative Z direction. Yeah, Z direction. So C is directed towards negative Z. So the question is find the force per meter on conductor C. So need to find the force that is exerted on conductor C due to conductor A and conductor B. Okay, so let us find the force one by one. Let's find the force due to conductor A. So force due to A, yeah? So force due to A, yeah? Right, so again, since this is related to a current, wired current, so again, we can simply use equation dF vector equals to I dl cross B. Okay, remember I dl vector is the element that experiences the force, which means that I dl vector here is the element on conductor C, while the B vector is the field density produced by conductor A. So in that case, I can write that I dl vector is returned to be 150, which is the current magnitude for conductor C, and the dl will be returned as dz in the negative Z direction, because we know that the current in conductor C is pointing towards negative Z. So we can say that the dl will be dz of negative Z direction. Whereas for the B vector, which is produced by conductor A, you can write it as mu naught of 75 divided by 2 pi, and we have a perpendicular distance from point A, from the conductor A to conductor C to be equals to 2 meters. So we have 2 meters there. Yeah, this is based on the equation of, if I can write for you, we have mu naught of 8, just mu naught of I over 2 pi r of P in the vector. Yeah, based on this equation. Yeah, so we have 75. R will be 2 and the phi will be L cross R. Okay, so let us find out what should be L and R then. So we need to rewrite them. So the dF here will be 150. Okay, 150 dz of negative z cross mu naught 75 divided by 4 pi. Yeah, L cross R. What is L? L is the direction of the current in A, which is Z direction. Z direction. Whereas the R, yeah, let me have a look then. Didn't have enough space then. Sorry for this. I need to write it here. Didn't have enough space. Okay, let us bring this L cross R here then. Yeah. So okay, L cross R. So L is the direction of the current for the A, which is positive Z direction, while R is this direction. That should be the R direction. Okay, and we know that from this diagram, the R in the vector is basically comprised of this vector and this vector. So we can write that the R in the vector is written as negative of y, this is negative of y, plus this component, this vector. So what is this vector then? So this vector is basically the vector towards positive x, and the magnitude of it will be 2 squared minus 1, which is set of 3. Okay, so for that, we're going to have that r unit vector will be negative y plus set of 3 direction of x divided by the distance of 2. So that should be unit vector of r. Yeah? And from here, we can have that L cross r will give us z cross negative y will give us positive x over 2 over 2 plus set of 3 z cross x will give us y over 2. So that should be unit vector. Yeah, unit vector for L cross r. So we're going to have it as x in the vector plus set of 3 y divided by 2. Yeah? And from here, we can proceed with the calculation of force per meter, basically. So we have dF vector equals to mu naught 150 multiplied with 75 divided by 4 pi. I can bring the dz to the left-hand side, dF over the dz, because the question asks us about force per meter. Yeah, so I can bring dz to the left-hand side. Okay, so we have negative z. So this is cross product basically. Negative z cross x over 2. So that will give us negative y over 2. Negative y in the vector over 2. Okay, plus negative z cross set of 3y over 2. So that will give us 0. Sorry, negative z cross y will give us positive x. So that will give us set of 3 divided by 2 in the direction of x. Yeah. Okay. So that should be the force, yeah, experienced by conductor C due to conductor A. Okay. So I think you can do the same for force on conductor C due to conductor B. Okay. So I think it will be similar. So F due to conductor B. Okay. So we're going to follow the same technique. Yeah, the same equation to be used. Yeah, but the difference will be on the B vectors. Yeah, because for the B vectors, basically the change will be on the direction for the B, which is the L cross R. So I hope that you can work out for that. Yeah, for us to calculate the total force, the force produced by site by the wired B or current B towards current C. And following that, we can just add these two answers together. The answers obtained from this solution and the answer produced from the second solution. So just add them together, and that will give us the force per unit length on conductor C. Yeah, so for F due to D, I think you can do it on your own. Yeah, because the method will be similar to what we have done earlier. Okay, so that should be the end of lecture 18, which is on the force, magnetic force principle. So in the next lecture 19, we're going to proceed with two topics, still in chapter 7, which is on the magnetic material and influence, which are on the materials and also on the magnetic boundary conditions.